Without question, the Allison engine has a set of die-hard fans, and it makes sense considering the engine's performance numbers and the things that it accomplished after the war. But considering its performance during the war, it is somewhat surprising that there are so many people that call themselves a 1710 fan. It was very comparable engine to the Merlin. Both were liquid-cooled V12s, and for some reason, the Merlin overshadowed it. Now that may be because the Allison had poor performance at altitude, and it could be for other reasons. Those are questions that we're going to answer today. For those that don't know, the Allison Engine Company got its start in Indianapolis when a man named James Allison started a small precision shop company that manufactured and designed parts for race cars. Those race cars would inevitably take part in the Indy 500. When World War I took off, James Allison and the Allison Engine Company found themselves in the military engine business. They needed an engine and they needed it fast. To accomplish this, him and a team of engineers locked themselves inside of a hotel room for 7 days, quickly designing what would eventually become the Liberty engine. It had some major drawbacks, especially for the time. Its automotive influence, based on James Allison's background, used things like coil ignition and a 45-degree cylinder bank offset, and the thing only made about 300 to 400 horsepower despite its massive 1,650 cubic inch displacement. The Liberty was by no means an amazing achievement of engineering. It left a lot to be desired, but it was the best we had at the time, and the Liberty was manufactured quite a bit. I believe 20,000 Liberties were manufactured and used throughout World War I and in the interim between World War I and World War II. After World War I, tragedy struck the Allison Engine Company when James Allison suddenly passed away from illness, and the company was sold to Fisher & Company, who was then presidented by Eddie Rickenbacker, the World War I ace. They only owned the company for about 3 months, though, until the company was then purchased by General Motors for $600,000 plus $200,000 of improvements. Shortly after the acquisition of General Motors, the very first engine designed by the company since World War I began. It was an X-type engine, it was about 4,520 cubic inches, but it was never really fully designed. It was never finished or flown. It was mostly just a blueprint. After that, the Allison Engine Company started working with the Navy extensively because at the time they were developing some absolutely massive airships, 2 of which actually were intended to be aircraft carriers, the Macron and the Akron. These both ended in disaster, were never used very much. I believe they suffered from some severe performance issues, and the Allison Engine Company was never actually able to make any ends meet, monetarily speaking, with these projects. The money side of things for the Allison Engine Company never really changed until we start getting into the 1930s, when the Navy started taking notice of some Schneider Cup. If you don't know what the Schneider Cup is, it was a very influential air racing series that happened in the 30s at the height of when air racing was popular. At the time, engines manufactured for these Schneider Cup planes were making incredible horsepower numbers. We're talking like 1.3 horsepower per cubic inch, which blows pretty much every production World War II aircraft engine out of the water. So how can that be? How can we be making 1.3 horsepower per cubic inch in the 1930s when we look at the performance data for all of the World War II production aircraft engines and they're not making anywhere near that? Well, you also have to remember that these racing engines were doing quite a few things to increase their power output that were not sustainable for what we need out of a reliable production aircraft engine. So when we're looking at a race plane, the total service life of this thing is tens of hours. It's not hundreds of hours or thousands of hours. So a lot of these engine designers, if we look at, for example, the DB601 that was used to set the airspeed record in the 30s, in Germany, it was, the speed of the engine was increased beyond a sustainable level. So the thing was going to tear itself apart in short order. It was also using what these air racers started using the term witch's brew, which was a special fuel that was not mass producible. And this would include isooctanes, aromatics. It would include a much higher octane that was, than was being mass produced in the average fuel at the time. It was also, a lot of them were using significant portions of alcohol as well. So the issue was, engineers knew how to make a very high specific power for a very short amount of time. The trick of engineering was designing something that could make 1 horsepower per cubic inch, but could also last during a reasonable amount of time in the field in a war environment. And that's where the Navy really got involved. The Navy wanted a company to take some of these lessons that the engineers had learned during these Schneider Cup races and try to implement them in a more conservative way, into a production aircraft engine. And that is when the Navy commissioned the Allison Engine Company to develop the very first 1710. That was the 1710-A. The Allison 1710A was pretty far off the Allison 1710 we know and love today. It was only making about 650 horsepower at 2,400 RPM, but it did have some very unconventional aspects to its design that put it head and shoulders among some of its peers, even the Merlin in some respects. Throughout the 30s, we can see that the Allison was just at least one step ahead of the Rolls-Royce Merlin, and we'll get more on that later. In terms of its general layout, the 1710 was a 12-cylinder liquid-cooled engine with a 5.5-inch stroke and a 6-inch bore. I don't know why I keep saying that backwards. It is a 6-inch bore with a 5.5-inch stroke. It had a 60-degree offset to monoblock cylinder banks, so these cylinders are set into a single cast item rather than an individual cylinder. It also featured some unconventional things like or at least at the time, it had a very good combustion chamber. It had what's called the pent roof combustion chamber, 4-valve layout with 2 opposing spark plugs. It did have removable cylinder heads. Those cylinder heads were removable by 14 studs that locked the cylinder head to the monoblock cylinder case. The valves were driven by a single camshaft that used roller rockers, which would turn out to be an excellent design in comparison to the friction pad that was constantly having issues and plagued the Merlin series. The cylinder liner was carburized hardened forged steel, which was shrunk onto the cylinder head. The coolant jacket had the interesting feature of a steel sleeve pressed into the corrugated section, which allowed unrestricted turbulent flow around the wet liners, but restricted flow between the jacket and the stainless liner. The crank was a 120-degree 6-throw and had 7 main bearings. To achieve proper rigidity, the 1710 used a one-piece cradle incorporating all 7 main bearing caps. The connecting rods were also of note. They were conventional blade and fork designs, however they were incredibly strong, so strong in fact that air racers found ways to use them in Merlins for unlimited air racing after the war. Reduction gearing in early Allisons was problematic. Despite Wright engineers telling Allison from the outset that an overhung pinion type system had never been successful, they chose the design anyway. What followed the overhung pinion gear was a series of design issues that followed and plagued the Allison until the 1710-F model, when they finally got their act together and switched to a conventional spur type gear. Let's talk about the Allison 1710's supercharger. The Allison 1710 had its own mechanical supercharger. There is a myth that goes around that there were unsupercharged or naturally aspirated Allisons that partook in the war, and that is not the truth. All Allisons were using forced induction. The A and the B models had a very small, puny impeller. When we get to the C model, which we're going to get into more in a second, the mechanical supercharger was enlarged, at least the impeller was enlarged. It made a little bit more power. But the main issue takeaway with the Allison's design was that the U.S. Army did get involved in the design process of the Allison very early on. And that's important because it was told to Allison that all applications of their engine could plan on having the General Electric Type B turbocharger coupled with the Allison engine. So the Allison engineers are assuming that they are making essentially the mechanical second stage of what would be a 2-stage system. They did not know that the reputation of their engine would be sullied by General Electric kind of dropping the ball with the timeline that they were able to produce these decent turbos. Also, nobody foresaw the fact that this turbo system was going to be enormous, and that many of these later, like the P-39 and the P-40 were going to be too small of an aircraft to actually house the General Electric turbo, which means they were going to be forced to use just the mechanical supercharger. And because Allison wasn't going to design a 2-stage system, or even, let's be real, an adequate single-stage system, because if we compare it to the Germans, it was pathetic, that was what handicapped the Allison's reputation. So we'll talk a little bit more about the conclusions that some of my references and resources have talked about. But this was a big problem. If, we can only imagine what might have happened had Allison been given the leeway from the outset to design their own forced induction system from scratch. The Allison 1710-B was much like the A model, but it featured some interesting changes. Namely, it had slightly more horsepower than the 600 horsepower variant. This one made 750 horsepower. The most interesting thing of the 1710-B was that it was going to be intended for airships. This was that brief moment in history that I discussed before, where airships were kind of a popular thing. That created some interesting design choices by the Navy. We have the increased horsepower from 600 to 750. The other thing that's important is the Navy has removed the supercharger and they're asking for a reversing gear. Now, I don't know how much you guys know of this, but reversing an engine is much more difficult from an engineering standpoint than simply having a transmission going to a reversing gear. The resulting design that Allison came up with was pretty ingenious. It could actually switch from forward to reverse in about 8 seconds or so. And this shifting mechanism that they designed had to do all sorts of movement within the engine itself, reversing the direction of the camshaft, changing the magneto, as well as the distributor finger. I always have to look at my notes for that last bit. I don't know why. The V-1710 was the first major redesign of the Allison engine series. It was the first engine, in fact, to reach 1,000 horsepower in military history. The main changes were a complete redesign of the supercharger. We now have a 9.5-inch impeller that is increasing the boost pressure, but the engine had many issues. As most engines we see, as their development history kind of increases and we see their horsepower numbers increase, we also notice that we have a corresponding fatiguing of various components, and that was definitely the case with the 1710-C. In 1935, the airplane went to a testing trial. It was put on an air-simulated air screw, and it is important to note that prior to this, Allison had never tested it on an air screw, just on a test stand. So when the engine at 1,000 horsepower at 2,400 RPM went through its 150-hour type test, it had a crazy amount of torsional fatigue that affected the engine that the engineers just didn't anticipate. So in 1935, the engine is being completely revamped once again to try to meet this test of 1,000 horsepower. That kind of became the number to beat. At first, they bring in Fred Duesenberg to have him, that's at least the legend, or so the references tell me, of automotive fame, to come in and work with the engine. But they eventually settle on a man named Ron Hazen, and Ron Hazen comes in to really clean house and try to solve some of these issues. They're having issues, unsurprisingly, after they've been told by Wright engineers that this wasn't going to work with their overhung pinion gear. Ron Hazen comes in and he swaps that to a internal shaft that is running inside the propeller shaft now. That is going to help, coupled with some clutches, with some of the vibratory modes that they're experiencing and some of the issues and wear and tear with that portion of the engine. But at this time in history, it seemed like once one issue was fixed, another one would crop up, of course. So they also end up changing the piston ring design, changing the valve timing, and decreasing the compression ratio from 6:1 to 5.8. The blower ratio was also reduced from 8.77:1 to 8:1. Also during this time, during the development of the C model, the intake manifold itself was redesigned, giving rise to the classic ram's horn design, which greatly improved the mixture distribution. Tragically for the Allison Engine Company, when they finally got all of these issues ironed out for the C model, they go back to the testing cell to do their type test on the air rig, and out of the 150-hour test, the Allison-C fails at 141 hours. What happened was the crankcase itself had a fatigue problem between the third and the fourth center, so the middle of the engine, which failed the engine and resulted in a penalized test. What was quickly fixed was the engine was brought off, and the crankcase was reinforced, and it came back with a strengthened crankcase and finally succeeded. This was in 1935, so the Allison 1710-C makes 1,000 horsepower, as I said, and which was of note because at this time, during the same time period, the Merlin was struggling to make its test at 990 horsepower. So 10 horsepower ahead of the Merlin, but technically, it's still ahead, even by just a hair. In 1937, the Allison Engine Company designed the -D model. The D model was designed for the XFM-1 Airacuda, which was a tragically very cool looking aircraft. Don't get me wrong, it was extremely cool looking, but it was just very impractical and didn't prove to be a great interceptor or a bomber escort, which is what it was designed. It was a twin engine pusher aircraft, which automatically makes it cool in my book because I love pusher aircraft. And so the prop shaft was extended. The Airacuda, just briefly touching on it, we'll have an application section towards the end of the video, but while I'm here, the Airacuda was slower than the bombers it was going to escort. It was a failed project, and while looking very awesome, was just not a practical design. Also of note, during the Airacuda 1937 days, the turbochargers finally start getting mounted on these Allison engines, and of course General Electric is having issues with the design. General Electric could probably be an entire video in and of itself, but the main issues that they were experiencing during the turbocharger design were metallurgic issues, so coming up with alloys that could withstand the incredible heat and the incredible rotational speeds that these turbocharger impellers were undergoing. So they were having lots of issues with the turbos exploding, essentially, which was generally not what you want when you're flying at 30-some thousand feet. In addition, while they were very good at producing components, probably one of the best. Their gas science knowledge was lacking behind some other countries, namely Germany. So they were doing some things that Callum Douglas notes in his book about having the inlet and the outlet pressure still be a 1-to-1, whereas most turbos at the time were having a reduced outlet to increase the velocity of the outflowing air of the turbo. Finally, we get to the V-1710 E model, which was mounted in the P39 era Cobra. The model of engine was used interestingly. If you know anything about the P39, it had a mid-mounted engine. To get that mid-mounted engine to transmit power to the propeller that was all the way up front, we used two 4-foot, 2.5-inch long extension shafts. The extension shafts ran up to the propeller reduction gearing, which was actually in the nose of the aircraft rather than mounted right on the engine itself. Extension shafts were mounted on a very reliable had roller bearings and were held in a cradle that was very well tested and designed, because the extension shafts ran right through the pilot's legs. So some failure of that drive shaft extension would probably not be good if things went poorly for that. Additionally, they also managed to fix some of the issues they were experiencing with the reduction gear system just by nature of having it external and away from the rest of the engine. In this case, they used, instead of the overhung pinion, they used a conventional spur gear. That spur gear was mounted to the extension shafts and running at crankshaft speed. Attached to this reduction gear system was also the gun synchronizers, the engine's governor, the hydraulic pump, as well as the oil pump for the reduction gear system itself. This time they also changed the supercharger design quite slightly because they removed the reduction gearing system from the front of the engine up into the nose. They needed a new way to pull power from that to drive the supercharger. To do this, they just ran a quill drive to the back of the engine and powered that from there. So the cams and the supercharger now are powered from the rear of the engine, which mirrors more conventional designs at the time. Finally, the V-17F model. It finally switched to a conventional type of reduction gear system. So all of these vibratory issues, various fatigue problems that are being caused by the overhung pinion gear system are finally designed out of the thing. To finish off the evolution of the models of the 1710, we end with the G model, which is the big daddy of 1710s. It unfortunately never saw service in the war. It missed out on entering the war, but it did have some incredible numbers. The V-1710-G achieved 2,200 horsepower at 3,200 RPM. It also made a piston speed of 3,400 feet per minute, making it the fastest production piston speed engine ever created. Let's talk about two-stage Allisons. Now, we mentioned that the Allison was always intended to be a two-stage engine. It was supposed to be coupled with the General Electric turbocharger. What Allison did partially through the war was to try to design a second-stage mechanical supercharger to remedy the poor altitude performance of the Allison that people were experiencing during the war. We could see that these altitude problems lost Allison several contracts. As we all know, or most of us know, I would assume, that the initial A model Mustang was powered by an Allison, and it was eventually switched over to the Merlin, Packard-built Merlin. That's also the case almost for the P-38 Lightning. The altitude issue was so severe at the time that General Motors actually had to lobby against the P-38 being switched over to the Merlin. Now, we know, and there's a very good video about how the Allison was performing better than the Merlin because of the General Electric turbo. If you're more interested in comparing what a P-38 Lightning would look like with a Merlin, or why it was probably better that they just stuck with the Allison, there's a great video on that over at Greg's Automobiles and Airplanes, where he talks about that quite extensively. It turns out the forced induction system is much more important than the engine itself. These engines are so similar that the better forced induction system will come out on top. Now, there are some things to be said, I think, in that particular discussion about the issues that the P-38 Lightning faced in Europe due to the cold climate, and we're going to talk about that more in the applications section. But there are some arguments that I think are valid arguments for maybe a Merlin-powered P-38, but that's beyond the scope of this here portion right now. So we eventually see the Allison Engine Company come up with a mechanically driven two-stage supercharging system. Unfortunately, it's just too little too late, and it doesn't get seen or developed into any aircraft that entered the war. Before I move on to the final applications of the 1710 and my kind of closing remarks about the engine itself, I want to talk about one innovation that the Allison Engine Company began testing in the early 40s that was absolutely insane, and that is turbo compounding. Now, I've mentioned turbo compounding before in another video, and people kind of usually get it, well, it's often that people get it confused between a two-stage turbo system. So they think about compound. The word compound is that I'm talking about a two-stage system. So either a supercharger combo or a super traditional turbocharger combo. I want to be completely distinct here. And what I'm saying is when I mention turbo compounding, and at least in respect to what Allison was testing and what they were designing at the time, I'm talking about a compressor that is being geared through a reduction gear system back to the crankshaft of the engine itself. So it is a power recovery device where we're using energy from the expelled exhaust gases to crank that energy through the compressor back into the crankshaft itself. Now, unfortunately for all of us Allison fans, of which I include myself, the testing for the turbo compounding system actually began in 1941, but the altitude performance of the Allison engine was so bad at the time that they had to take all of their energy away from developing the turbo compounded system to trying to remedy and implement a two-stage supercharger system before the end of the war, which seemed to be more practical and required less design work. Had they continued and were able to finish a turbo compounded design Allison before the end of the war, I think it would have become hands down the most mind-blowingly powerful engine that we saw during the war, bar none. I mean, even, save for the jet, it literally would have just blown people's minds. At 11,000 feet, the turbo compounded 1710 made 3,000 horsepower at 3,200 RPM at 100 inches of manifold pressure. So, I mean, again, I might bring up on the screen here if I do the math, what those specific power numbers are for the Allison 1710. And again, I don't really know what the turbo stuff weighs, so it's going to be a little off, but it's going to be, give it a reasonable error of like plus or minus 10%. I think even with the plus or minus 10%, the numbers are just absolutely mind-blowing, because 3,000 horsepower out of an engine that I believe is like 1,700 pounds is just, it's insane. It's coming up on 2, so quite crazy. As I said, had this engine been developed and implemented in time to make a difference at the war, before the war's end, it would have just been an absolute game changer for all of the Allied aircraft that used it. The 1710 was in the FM1, the XP-37, the P-39, the P-40, the P-38, and the P-51. The reputation for the P-40 of an underperforming aircraft early in the war, despite its good track record, especially in China with the Flying Tigers, was largely due to what we were talking about before. The P-40 was an aircraft that could not handle the size of the General Electric turbo. The Type B turbo system and its ducting was too large for the Allison. To be coupled with the Allison inside of the cowling of the P-40. So the performance at altitude was not ideal, and the single-stage mechanical supercharger could not generate the boost pressure that would have been required for the Allison to make more horsepower even at sea level. So issues with the P-40 and its performance were not ideal. Now, late models of the P-40, I do believe, finally did get respectable top speed numbers, but it was, again, too little too late, as they were finally given a more decent two-stage supercharging system. Let's talk about the P-38. Now, the P-38 got a poor reliability record and was not seen as a good aircraft in the European theater. As we all know, or at least I would hope most of us know, in the Pacific theater, the P-38 was the star of the show. Dick Bong was the leading ace of all of the U.S. pilots in the entire war and got the most victories in a P-38 Lightning. The difference between the reputation of the P-38 in the Pacific and the reputation of the P-38 in the European theater came down to temperature. The problem was the calibration and the temperature windows of the aftercooling system, or the intercooling system, for the turbochargers in the P-38 did not like the cold air in Europe. Between the 20,000 and 30,000 foot altitudes that the P-38 was operating in, overcooling of oil in the intercooler caused oil foaming. Eventually, this would cause issues with the turbos itself and issues with rods breaking down and other various forms of engine problems just because of oil starvation. So what really needed to happen was more of a carefully engineered system of controlling the oil temperature in these components in the frigid airs of the P-38 in the European theater. Now, other issues included from the P-38 that are kind of like not related to the engine included. It had terrible heating just for the pilot. So they hated the P-38 in Europe just because the pilots are freezing. They literally have to be pulled out of the cockpit after their engines because, again, there's no engine, keeping you warm that's mounted right there in front of the firewall. So people are, they're just getting insanely cold. Now, the P-51 initially was using an Allison engine, and as we all know, it was switched over to a Packard-built Merlin design because it needed to be a high-altitude fighter. Now, that was the right choice, absolutely, at the time, because of the U.S. Army's meddling with the engineering behind the Allison engine and not allowing the Allison engineers, initially at least, to build a two-stage system or really to plan on spending much time. I mean, they were essentially promised that the forced induction system will be handled by General Electric. Don't worry about designing a super amazing supercharger. Don't worry about, really hashing much of these design problems out, because we'll handle that on our end. So you have to also not fault the engineers at Allison for having this engine that didn't perform well at altitude. So eventually, as we know, the Allison was swapped out of the P-51 for the Merlin. So at the end of the day here, what were the main advantages of the 1710? If you were an aircraft manufacturer and you knew everything, and you wanted to decide between, say, the Merlin or the Allison 1710, what would we highlight as a salesman for the Allison 1710? Well, the Allison 1710 has better bearings for its camshafts. You're going to have less engine wear from the roller bearings in the camshaft. Compared to the friction pad of the Merlin engine, the Allison 1710 is going to experience less wear. The Allison engine company was also known for its main bearings on its crankshafts, and these led directly to the Vanderbilt bearings that would be used on the Napier Sabre, as well as the in Formula One racing after the war. So very good main bearings, and they were incredibly strong. Additionally, the combustion chamber of the Allison 1710 was incredibly well designed. I think Callum Douglas points out in Secret Horsepower Race that the low, narrow squish zones of the pent roof combustion chamber, had the 1710 capitalized on this, which they did not, but they were I think he quotes, frustratingly close to a combustion chamber that probably could have tolerated at least 4 atmospheres of manifold pressure without experiencing knock. Now, the engine did not experience that a level of anti-knock capability, and that's because there was some fundamental design that was slightly off. But the point here is that it was very, very close to enjoying this benefit. So those would be some of the things that we would point out for the Allison as advantages. Now, disadvantages were numerous. Again, to close out the whole video, I mean, the main mantra of this video is that Allison should have been allowed to design its own supercharging system. Had the engineers at Allison followed some of the research and development going on at Rolls-Royce, used some similar design aspects of the Rolls-Royce supercharger in its own, it may have been, and it likely would have been the case, that the P-51 never had to switch over and license Rolls-Royce engines. Additional disadvantages were other things. The scavenge pump, the oil scavenging pump in the engine was not running at a high enough rate compared to the main oil pump. So there was an abundance of oil in the engine crankcase. It was kind of contaminating into the combustion chamber. And when you have oil contaminating the combustion chamber, you're having your anti-knock capability also reduced. As we saw, again, the big elephant in the room is turbo compounding. I think we'll close the video there. Had the engine been developed with turbo compounding, which you have to respect Allison for switching, for choosing the practical, more well-known technology. They probably in 1941 were not aware if they could finish the turbo compounding design in time to end the war, so they went with the more practical design choice of developing the two-stage supercharger, which was obviously very much in need for the engine. So, did they make the right choice? Yes. Do I wish they would have developed turbo compounding, and had we seen a fighter in World War II that used that technology? Absolutely. I think that really is where we see Allison engines kind of go nuts after the war with these 3,000 horsepower numbers. So thank you guys. I hope you enjoyed this video. I hope you enjoy this new format. We're trying something different out with the channel. We're trying to increase the production quality as much as we can, considering the massive inflow of viewers and subscribers. So if you do like this new format, please don't forget to let us know in the comments. And again, like and subscribe. Thank you guys. See you next time.